Okay, welcome to lecture, and we'll get started here in just a sec. Continuing on with chapter 8, I believe. Like usual, again, if you have any questions, please feel free to ask them in the box, and we'll pick up where we left off. Okay, so last time we started getting into chapter 8, which is solutions, and a couple of things we talked about. Remember that basically a solution is made up of two things. There's the solute and the solvent. And when we talk about the solute is usually the smaller part of the solution, and the solvent is usually the larger part of the solution. So in a traditional solution, for example, if you took some solid sodium chloride and you dissolved it in some water, the sodium chloride would be the solute and the water would be the solvent. And as we talked about, water works really well as a solvent for a lot of things, um, especially ionic compounds, polar compounds, and that's because water is polar. So it gives it a place to interact with what it's trying to dissolve. And again, a solution is typically the guys that will get that AQ symbol next to it. And again, that AQ symbol means aqueous. And again, the name of the solution is usually the solute as well. So as we talked about last time, for example, if you had a sodium nitrate solution, the sodium nitrate would be the solute, and most likely the something like water there, because it's ionic, would be the solvent. And again, as we talked about last time, that is the difference, between something like that and something that has just like H2O that has just the L next to it. The L next to it, again, implies it's a pure liquid, which would imply that nothing pretty much is dissolved in it. So you just have H2O by itself, as opposed to the sodium nitrate solution, where you have water and sodium nitrate together to make that solution. So that's really the big distinction between something that's aqueous and something that has the L symbol or liquid. Again, one is sort of a mixture of two things, because that's basically what a solution is. It's a homogeneous mixture, and a pure liquid obviously is just one substance by itself. We also started talking about, I believe last time, a couple other things in terms of involving solutions. We talked about electrolytes. Electrolytes are substances that when they go for basically a swim, like in water, they will break apart into ions. And the breaking apart into ions is important in terms of its ability to pretty much conduct electricity. So we had strong electrolytes. So most ionic compounds, strong acids, strong bases, or strong electrolyte. So if you did have something like a sodium chloride solution, in a sodium chloride solution, pretty much what you would have in that solution is pretty much here 100% of their ions. So 100% of what you would have in that solution is the ions, and you would have none of the whole units still together. And that would be considered something like a strong electrolyte. It's a strong electrolyte because, again, 100% of it breaks apart into ions. You produce a lot of ions in a very short period of time. And again, those ions are going to be very important in terms of conducting electricity. And it can conduct electricity a lot based on that presence of all those ions. So we talked a little bit about an example of like a light bulb connected to some electrodes. And again, if you sort of put that light bulb that connects those electrodes into a strong electrolyte solution, the light bulb would go off and be very, very bright. We also have like a weak electrolyte as well. Weak acids, for example, weak bases are also weak electrolytes. And the difference on that is they will also, for example, here, hydrofluoric acid will also break apart, but in solution, you mainly still have the whole thing together, but you do have a little bit of these guys that are being produced. So since it's still able to sort of break apart in solution, it's still considered electrolyte. It's still able to produce some ions, but nowhere to the extent of a strong electrolyte, for example. And because of those little bit of ions that are in solution, it's still able to conduct electricity. So going to that light bulb example, like we talked about last time, the light bulb would come on, but it'd be very dim, so not as bright, obviously, as, say, a strong electrolyte. And again, mainly in solution, you would have the whole thing still together. One way to sort of recognize it usually in a reaction is by the arrows. So a strong electrolyte like on top there pretty much has a one-way arrow heading towards the products, which means nobody's coming back the other way. 100% of everything is dropping into the product side. While you have these reversible reaction or arrows heading in both directions, and that implies, again, a reversible reaction where some goes to the products, some comes back the other way, and at some point it does reach chemical equilibrium, which means that, like we talked about in the last chapter, we essentially do have a little bit of everybody there, but it will basically, the rate of the forward reaction will equal the rate of reverse reaction. I spit that out right. Let me try that again. The rate of the forward reaction will equal the rate of the reverse reaction. So it's a good question about covalent compounds, and we're going to talk about that actually right now, like we did last time. There are some compounds, and a good example of that would be, say, something like sugar, that technically, again, are carbons, hydrogens, and oxygen. So these are covalent compounds. And sugar, for example, as we know, if you take it in something like water, will dissolve, and it will dissolve in it. But the key here is because it's covalent, it basically will produce no ions, yeah? So although a non-electrolyte, which is what we're sort of talking about here, for example, you know, they have the ability perhaps to dissolve in something like water, like sugar could, but because something like sugar, which is carbon, hydrogens, and oxygens, all kind of covalently bonded together, will not produce any ions. And that's the key to sort of the conducting electricity and so forth, is the idea that it doesn't produce any ions. And because there is no production of ions, it will not conduct electricity. So you definitely can have you could have covalent compounds and so forth that obviously are soluble in water, dissolve in water, like sugar, like something like, for example, methanol, which looks something like this. You know, it's able to be sort of soluble in, say, something like water and mix and everything like that. But the key is when they do that, it's not going to produce any ions and it won't be able to conduct electricity. So those things would most likely, in most cases, even if it has the ability to dissolve, um, but it doesn't produce ions. And again, that's the key part of it. It would be considered a non-electrolyte and probably wouldn't be able to conduct electricity. Other questions about electrolytes there? So we finished up on the idea of what's known as equivalence. And equivalence is one way that sometimes concentration of solutions are sort of displayed, especially sort of IV type solutions and stuff like that that contain ions. And equivalents are really based off of the idea of the charge of those ions. And it is simply from the charge where you can kind of get your equivalent sort of relationship. So for example here, something like sulfate, the charge on sulfate is -2, and really the minus or positive doesn't really matter when we're talking about equivalence. It's actually the number itself. So we could say in 1 mole of sulfate, there is 2 equivalents. And again, that comes from the actual charge, not the actual positive or negative part of it, but the actual number. And again, you can use that as sort of a conversion factor like we did sort of in the problem that's on the screen. 1 mole of sulfate would give you 2 equivalents. Our alternative 2 equivalents will give you 1 mole of sulfate. So equivalents per liter and milliequivalents per liter are very common sort of units of solution, especially, like I said, IV type solutions. And as we talked about above as well, milliequivalents to equivalents is really the same sort of conversion as milliliters to liters. So there's 1,000 milliequivalents in an equivalent. And it's very common sort of unit of concentration. So as you can see here, you know, we could use that in this particular problem. We were actually given the milliequivalents per liter here as 154. And again, we can use it really as a conversion factor to figure out how many equivalents there may be in a solution and so forth. So, for example, you know, if we had something like 0.025 moles per liter of something like calcium, calcium chloride, for example. And we wanted to know, you know, how many equivalents per liter that would be for each of the ions, the calcium ion and the chloride ion. We can sort of use this as a way to figure it out and just think about it like a conversion factor. So as we see before, when we take something like calcium, I don't know why I want to write that L first. Try that again here. Grab me an eraser here. All right. All right, so if we look at this, the solution of calcium chloride, and again, I just want to write that L first for some reason today. All right. When it does break apart, it breaks apart into a calcium ion, and in solution, we'd actually have 2 chloride ions that are there. And if this guy here, the whole thing together was 0.025 moles per liter, we could figure out sort of the concentration of the calcium ions by a relationship of how it breaks apart. It breaks apart into a 1-to-1 relationship here. So for the calcium, it would actually be the exact same number. But when we look at the calcium chloride to the chloride here, it's a 1-to-2 relationship. So we would have to multiply this by 2. I'll explain more about that a little bit later on, actually, in this lecture. And the concentration really of the chloride would be 2 times 0.025, and we'll get 0.05 moles per liter. So if we do sort of our calculation for each of these guys, we do see that on the screen here. We did it actually last time. We can, for this guy here, for the calcium, come up with this relationship that 1 mole of calcium ions will give you 2 equivalents. For the chloride, we can see that for 1 mole of chloride, we would get 1 equivalent, again, because the charge here is -1, which means it's 1. So if we looked at the calcium ions, we see that 0.025 moles per liter of calcium. We can use our conversion factor here, which is right here. And we can use 1 mole of calcium will give me 1 equivalent in this case, which would give me 0.025 equivalents per liter for the calcium part of the solution. We could also do it for the chloride part. And again, we would start with the concentration of chloride in there. And again, we would use the equivalence part here as a conversion factor. So to get rid of the moles, we see that 1 mole, I'm sorry, that should be 2 equivalents. Some bad math there. Try that again. There we go. I boxed it and everything, missed the whole 2. Let's try it here. All right. So my bad. About here, the calcium, obviously, as we can see here, is 2 equivalents, and that would give us 0.05 equivalents per liter. That's better. And this would be 1 mole of chloride, gives us 1 equivalent, and that would give us 0.05 equivalents per liter. And just to finish up about equivalence, as we were talking about last time, what we see is when we look at a solution, for example, that's ionic, that contains 2 ions in it, like calcium chloride, when you calculate something like the equivalents per liter, and if we were to convert both of these into milliequivalents per liter, they both would end up with the same number. And that always happens when you do these calculations. If you calculate either equivalents per liter or milliequivalents per liter, the concentration in terms of those, the ions in an ionic solution and equivalents per liter and milliequivalents per liter, should always end up being the same for each ion. And as you can see here, that's what we ended up with for our calcium ions. It's 0.05 equivalents per liter. For our chloride ions, it's 0.05 equivalents per liter. And that's because when we do any type of ionic compound, we always balance the charge, right? Which means as a whole, when we take an ionic compound, as a whole in that particular solution, the overall positive charge is balanced with the overall negative charge. And that's what's reflected here when we look at the concentrations of each of the positive and negative guys. The positive guys in a calcium chloride solution would be the calcium, which has an overall sort of concentration of 0.05 equivalents per liter, while the overall negative charge in that solution would be the chloride, which also has an overall concentration of 0.05 equivalents per liter. So one way you could kind of check yourself when you do sort of calculations that involve equivalents per liter or milliequivalents per liter, like I was talking about, I think at the end last time, was when you do calculate those concentrations for each of the individual ions, they always should end up being the exact same number for both ions if everything was done correctly. Any questions on equivalence? And again, that's what we were talking about, I think, at the end last time here, where if we had something like a sodium chloride solution in this particular example, because we know the concentration of the sodium ions is 154 milliequivalents per liter, because everything would be balanced in that solution, the chloride ions would also have basically the exact same concentration. Any questions on any of that there? All right, then let's talk about solubility. So solubility does mean basically if we take a solid, say in a liquid, the solid would dissolve in the liquid and make a solution. For mixing, say, 2 liquids together, sometimes that's what's referred to as being miscible. When 2 liquids mix together and are soluble, people refer to it as being miscible. And if they're insoluble, 2 liquids, for example, they're known as being immiscible. Liquid's a little bit different than solid and a liquid. Obviously, if you have 2 liquids together and you put them in and they mix, everything will look the same throughout. If you have 2 liquids and you put them together and they don't mix and they're immiscible in each other, that's typically where you'll see these different sort of layers occur. So when we talked about the solubility basically is how much solute can be dissolved in a given amount of solvent. And usually we'll oftentimes talk about it, especially if it's a solid sort of in a liquid, this is how many grams we could dissolve in 100 milliliters of solution, basically grams per milliliter if you want to think about it that way. And solubility is based off of temperature, as we will see. So temperature is an important part of sort of solubility. At a given temperature, there's really a maximum amount of solute you could get to dissolve in a particular amount of solvent. And depending on how much is sort of dissolved, we do get a couple different types of solutions. The first one is what is referred to as a saturated solution. And in a saturated solution, you have basically hit the maximum number of grams of solute that will dissolve in that solvent at a given temperature. So it's kind of like an example of sugar, for example. If you take some sugar, it will dissolve in water. If you continuously add the sugar, most of it will dissolve. But at some point, if you grab the big box of sugar and you just kept dumping it into, say, a glass of water, at some point there is a limit to how much, say, sugar you could get to dissolve in that. And if you dump perhaps the whole entire box in, or most of the box of the sugar in, at some point the sugar will stop dissolving and you'll end up getting it just sort of piling up on the bottom. And at the point where it officially sort of stops dissolving, the last little bit of the solid that will dissolve, that is basically what is known as a saturated solution. And what that means is once the solution becomes saturated, you basically have hit that point that no more solid will dissolve. So again, if you decide, I just want to continue to dissolve something, and you put more solid in, it will not dissolve at that point. Now, different than that is what is referred to as an unsaturated solution. In an unsaturated solution, you basically haven't hit that point yet. So you haven't hit the point of the solid, for example, not dissolving, and that's known as an unsaturated solution. So an unsaturated solution, if you take more solute, so for example, say you take some more sugar or something, at that point and you put it into that solution, the sugar will continue to dissolve. And it will continue to dissolve basically until it hits what is sometimes referred to as its sort of saturation point. And basically at that saturation point, you pretty much have now a saturated solution. So an unsaturated solution, solid will continue to dissolve. It will continue to dissolve until you hit a saturated solution. And at that point, no more will dissolve. A third type of way that sometimes solutions are classified as is what is sometimes referred to as a supersaturated solution. And in a supersaturated solution, you pretty much have too much solute dissolved in the solvent. So in a supersaturated solution, you've essentially achieved a solution where it looks like a solution. It sort of has liquid features, if you will. You don't see any solid in it, but you've created a solution where you managed to get way too much of the solute dissolved in that solvent. So a very common way that a supersaturated solution can be made is a lot of times you will make a saturated solution. And when you take that saturated solution, you'll sometimes heat it up. And typically, as we'll talk about, if you increase the temperature, what that allows is for you to dissolve more solid, for example, in a solute, in a solvent. And sometimes they'll say if something's not dissolving, just warm it up a little bit, and that'll allow it to sort of dissolve the solid. And by heating it up, you're able to get more solid dissolved. And then typically what you do is after you heated it up, you let it cool down. So after you got more of that solute to dissolve in it, you take that solution after it's been heated and you let it cool down pretty much by itself, undisturbed. And a couple of things happen in that process. As you're heating it, you're obviously, for example, not dissolving, but evaporating off some of the water, and that's sort of the solvent. So you're losing a little bit of that solvent. But as the solution really kind of cools back down, at temperature 1 over here, we'll call it temperature 1, at the hot temperature, you could get a lot more of that solid to dissolve. But at temperature 2, which is the cooler temperature after it kind of cools down, you now have that stuff that's still dissolved, but it can't really be dissolved at that point, because at the cooler temperature, you should only be able to dissolve less of it. So what you end up having through this process is a supersaturated solution over here. And inside here, you pretty much have way too much solute in that solvent. And again, because you cooled it back down, and now it's like, whoa, I got way too much. And what it actually becomes is a very sort of unstable solution. Although it will look like a solution at the beginning, it's so unstable that if you just kind of knock the test tube a little bit, like tap it with your finger, it's enough to make all the solid pretty much come out of solution. And what you'll see is all the solid will just slowly work its way out of the solution, because it realizes it has too much already dissolved. And it'll go from a sort of solution, liquidy, to rock hard solid in just a second. Even if you don't tap it or something like that, but you take just like this much, this long circle, this very small piece of whatever you dissolved in there. If you just drop that one little kind of crystal into that solution, again, what you would eventually start to see is it would be a liquid. And all of a sudden, once you drop that in, you'll start to see like all the solid, it will start building and building and building. And then this entire thing would just become a rock hard solid, basically. And it's a really sort of unstable solution, if you want to think about it that way, because of the fact of how it was made. You ended up getting way too much solute dissolved in that solvent. Any questions on that? So let's talk a little bit about then solubility. So solubility can be summed up with the idea of like dissolves like. So we talked about some intermolecular type forces, and like dissolves like means that things that have similar ways to interact with each other typically will be soluble in each other. So when we talk about that, ionic guys and polar things are soluble in each other. Polar guys and polar guys are soluble in each other. Nonpolar and nonpolar guys are also going to be soluble in each other. And that's because they're able to interact with each other really well. So you got ionic and polar and polar and polar. Those guys could do some type of dipole-dipole interaction. They could do hydrogen bonding interaction. Our nonpolar guys, they could do some dispersion forces interactions. But you really only get sort of in trouble when you try to cross over and take something that's polar and mix it with something that's nonpolar. They're pretty much insoluble in each other. So if you take something like oil and water, they do not mix. Water is polar. And again, polar means it's got a positive, negative side, right? Oil is pretty much carbons and hydrogens, which is nonpolar, which means it's essentially neutral. It has no charge. And if you remember, the intermolecular forces basically work with each other by the idea of opposites attract. So our nonpolar guy, our oil, will try to use dispersion forces, while something like water, which is polar, will use something like hydrogen bonding. And again, over the long period of time, they have no way to interact with each other. And that's typically why, again, we see if you had some water and you put some oil in there, the oil typically will just kind of float on top of the water. They don't really mix. For the short period of time, they could sort of interact with each other, but over the long period of time, they're really not able to interact with each other very well. So for example, if you think of like oil and vinegar, sort of salad dressing, something like that, you take it and you can mix it right before you put it on your salad. And, you know, it mixes fairly well. But then if you kind of put the bottle on the table at some point, what you see is everybody will sort of separate out from each other. And again, that's because over the long period of time, they have no really long way to basically interact with each other and stay together. But over a short period of time, they could kind of interact with each other. So as opposed to that, ionic and polar things using dipole-dipole type interactions, they could interact with each other for a long period of time. Polar things also, dipole-dipole or hydrogen bonding, can interact really well with each other for a long period of time. And nonpolar and nonpolar things, again, are going to be using the same intermolecular forces like dispersion forces. So again, it gives them sort of a long range way of interacting with each other. And that's really important for solubility, is basically things having the ability to interact well with each other. So if we have some small molecules with oxygen or nitrogen, they can hydrogen bond with water and be soluble. So sort of back to the earlier question here, this is a covalent sort of compound here. This is ethanol. And if you draw ethanol, it looks like this. And if you draw water, hopefully you know, it looks like this. A little to the right, those dots. But when we look at something like ethanol, for example, or methanol, in our earlier sort of example we were talking about, there's actually two parts of this. It's sort of an organic compound. And this part over here, it's all carbons and hydrogen, and it's pretty much nonpolar. But we do have this one bond here on ethanol, and this bond is an OH group. And based on electronegativity, it is a polar bond. So the oxygen is more negative. Again, the hydrogen here is more positive. Now, water itself overall is polar. And what that means is in water, the oxygen is more negative, the hydrogen is more positive. And even though ethanol here has a nonpolar part, because it does contain this little part here that is able to basically interact with water, and that's how it interacts. The oxygen, for example, in methanol is able to hydrogen bond with the hydrogen over here in water, and we make our hydrogen bond between those two. And because they have that little bit of interaction, that makes something like ethanol soluble in water because it does have that OH group. Same thing like what I was talking about earlier. We had our methanol, which looks like this. Also has that OH group that gives it a place to interact with something like water. So it is soluble in water. These things, solubility does decrease though. So for example, if you had kind of the same molecule, and again, all these are hydrogens. Now, although they do look very similar, the difference here is this guy's solubility would be extremely smaller, if any, in water. And that's because when we look at sort of the nonpolar part compared to over here and over here to this guy, it's much, much larger. And it sort of gets in the way of that OH group and the ability of it to interact with water. And the solubility really does start to decrease a lot. So typically it's something like this, which is an organic compound, which is an alcohol. If you get above sort of 6 carbons attached to that OH group, the solubility goes down a lot. But upwards of 6 carbons attached in sort of the box area, if you will. So upwards of 6 carbons sort of attached in that box area will be fairly soluble in water, again, because they're relatively small, and that's why it says small neutral molecules. Are able to interact with water. Again, if you get kind of that nonpolar part too big, it gets in the way, just physically sort of gets in the way of allowing water molecules to sort of come in there. Nitrogen as well, something like NH3, which looks like this, as we maybe talked about earlier, also has the ability to hydrogen bond. So remember that hydrogen bonding, the ability to hydrogen bond, you basically need a hydrogen that's attached to a nitrogen, oxygen, or fluorine. So those really electronegative atoms. and those guys would have the ability to hydrogen bond. So they're in ammonia, the nitrogen is attached to hydrogen. It's actually a polar molecule and will give it a way to interact with something like water as well. Nonpolar molecules are soluble in nonpolar solvents as well. So octane will dissolve in CCl4 because of dispersion forces. So if you had something like octane or hexane, which is just 6 carbons in a row. So if you had something like hexane, which is 1, 2, 3, 4, 5, 6. And again, if you look at it, it is pretty much all carbons and hydrogens all the way across. This guy is definitely going to be nonpolar. So this is nonpolar, which means, again, it's going to want to use dispersion forces. And it basically has no charge. It's neutral. And again, if you take something like water, which is polar, having that negative and positive side, they have no way to interact with each other for the long haul. But if you take something like carbon tetrachloride, like on the bottom there, if you remember from geometry and Lewis structures, this is a symmetrical arrangement. Everything attached on the outside is exactly the same. So everything's going to cancel out in terms of dipoles, which means this would be a nonpolar molecule. That's your tetrahedral geometry where everything attaches the same, and that gives you a nonpolar molecule. So carbon tetrachloride, which is nonpolar, works really well with hexane because they both are going to be using dispersion forces to interact with each other. And again, those temporarily kind of weak forces, but they're both using basically the same model of bonding to each other, and that allows them to be soluble in each other. Again, if you try to throw hexane into water, you're taking something that's nonpolar and polar, and in that case, over the long period of time, they will not mix. They will be immiscible in each other. You'll have the hexane up on top, and you'll have the water end up being on the bottom. If you look at it like in a test tube, you'll see these different layers that basically will occur. Any questions on that there? All right, so when we when we do make a sort of solution, more energy than is required to separate the molecules, the overall process would be exothermic. And when the separation of particles require more energy than is released, it's endothermic. So in terms of energy, same idea as what we talked about before. If the overall process, when you make a solution, for example, releases energy, it's going to be exothermic. And if we had to separate, for example, particles, the process would be endothermic to allow them energy. Again, really how a solution happens, for example, when we have an ionic compound, very badly drawn three-dimensional picture, does not look anything three-dimensional. But if you have an ionic solid here, they're basically hooked together in this very ordered arrangement. And basically what happens when something goes to dissolve is we have water molecules. They kind of come in and pluck off an ion, right? And then the positive ion gets surrounded by a bunch of waters. Then the negative ion gets surrounded by a bunch of waters, right? By the way, when they surround the waters, the negative ion is attracted to the hydrogen part of water, while the positive ion is attracted to the oxygen part of water, which is negative. And when we do this, that's basically how something dissolves. Basically, water molecules come in and pluck off the ions and surround the ions with water, basically, in solution. And that's really what the aqueous means, is like really this situation here. We have these ions that are floating around. Although they're floating around freely, they technically are surrounded by water molecules. So as these guys come in and keep plucking these sort of ions off, everything will eventually dissolve, for example, and we'll look at it and it'll look like everything disappeared when you take a solid and you dissolve it in water. But really what's happening is all those ions are getting trapped into the water sort of network, and it sort of disappears from our eyes. They're still there, and we know that they're still there because, for example, if you took a sodium chloride solution And although basically it looks just like water, right? We don't see anything in the solution. The sodium and chloride ions, the positive and negative guys, they're still here. They're just surrounded by waters at this point. And the water does basically two things. It allows everything to dissolve, and it also keeps these two ions away from each other, because the attractive force between the positive ion and negative ion is extremely strong, and they would want to come back together. But because we have the water there, it basically keeps them separate from each other, and we aren't able to actually see them come back together. But if you take sodium chloride water, for example, and you do heat it, what's going to happen is as you're heating it, these water molecules are going to start to evaporate. And once we start heating it and these water molecules basically evaporate, they no longer are going to be in the way of those two ions coming back together. And as we start to evaporate off the water part, those ions are now free to come back together. And as you would continuously heat it, and maybe you've heated a sodium chloride solution, what you'll be left with at that point is, after you evaporate off the water, is that solid, which is your sodium chloride back together in sort of its original form here. So the process of sort of making a solution is, you know, these water molecules, for example, come in, they pluck off each of these solutes, they surround the solute, and it sort of disappears, like it's gone. But again, it's really not gone. It's just sort of trapped in that water network. We help the sort of solution process along a lot of times, because when we're trying to dissolve something, usually what we do is pick up something and start stirring it, right? We start stirring it and mixing it. And as we sort of do that process, a couple of things we're doing as we're kind of mixing it, right? We are obviously throwing a lot more water molecules all over the solid, right? So more surface area is getting exposed to the water a lot quickly. And we're also adding energy when we do that, right? So we're adding some energy, which is this process right here. And we're putting a lot more energy in there, which allows everybody to sort of break apart a little bit quicker and get that sort of dissolving process occurring. Any questions on that? Now, there are some rules that help us decide, again, whether or not, if we sort of mix together some ionic compounds, for example, you know, would we expect a solid to form or not? And these are really what are known as sort of solubility rules. And these solubility rules help us determine whether or not we would expect a solid to form, or we would expect maybe not a solid to form. So look at this chart. So a little bit, maybe a clearer. So when we look at these sort of solubility rules here, these are typically the solubility of things, ionic compounds in water. So if you see a formula that contains anything that has group 1 in it, it's going to be soluble 100% of the time, which means it will get the aqueous symbol. So something is said to be soluble, it gets that aqueous symbol, that AQ symbol. If something is said to be insoluble, it gets that solid symbol next to it. So if you see a formula, an ionic compound, and it has anybody from group 1 of the periodic table, sodium, potassium, lithium, all those guys, that is always going to be soluble, should be aqueous. Same thing if you have anybody that contains ammonium, which is NH4 in it, will also be soluble 100% of the time. Things that contain nitrate, chlorate, and perchlorate also, if you see it in the formula, will be solid 100% of the time. Now, most things that contain chloride, bromides, and iodines, they are soluble in everything, but there are 3 exceptions: silver, mercury 1, and lead 2. And those exceptions mean that if you have one of those 3 exceptions, it actually will be insoluble and will become solid. If you don't have one of those exceptions, those guys, when they do mix, would become aqueous and dissolve. Now, most sulfates, except for calcium and sulfates, which are slightly soluble, will be soluble in most cases. Slightly soluble in most cases usually means more on the insoluble side. But usually we think about it in terms of soluble and insoluble. Now, there are certain things that are usually insoluble, and these are things that would typically not mix well with water. Hydroxides are insoluble. The exception, though, are alkali metals, which is the same exception we saw on the previous page. That's group 1. Barium, calcium are slightly soluble. Carbonates, phosphates, and sulfides are typically insoluble. Again, the exception would be the same exception we saw on the last page, group 1, and there's our ammonia, right? So how this works, for example, is if you had a formula like you took some sodium nitrate and you mixed it with some, that's not what I wanted to say. I'm batting 1,000 today with formulas. Let's try this again. All right, take 2. Here we go. Let's say we actually took silver nitrate is what I was trying to write there. Silver nitrate. And we mix it with sodium chloride. This would do a double displacement reaction, which would give you sodium nitrate plus silver chloride. And we can use our solubility rules to help us determine what should be a solid, what should be aqueous. So here, if we look at these two things, this is silver and nitrate. And if we back up here, here's nitrate, which means it's soluble in everything. There's no exceptions. And silver, we don't really see by itself, but because we do see nitrate in this formula, we automatically know that this should be a solution and it should be soluble, and it would get the aqueous symbol. When we come over here and look at sodium chloride, sodium, which is group 1, which again, if we go back to the last slide here, everybody in group 1 is going to be soluble. There's no exception at all, which means as soon as we see that sodium in there, we will automatically know that this also should be soluble and get the aqueous symbol. We could even look at the chloride if you want in this case. The chloride here is soluble in everything except these 3 guys, silver, mercury, and lead. And in the case of sodium chloride, that is obviously not silver, mercury, or lead, which means it is also soluble. So in that particular case, you could look at either one and help you determine, is it going to be soluble or not? Now going to the other side there, we have sodium and nitrate. So as we just saw, sodium is soluble in everything, and so is nitrate actually. So this also would be a solution. Now when we come over here, we see chloride, and chloride again is soluble in everything, but there is 3 exceptions, and one of the exceptions is silver. So again, if something is typically soluble in everything, it would get the aqueous symbol. But an exception would mean it would go from soluble to insoluble, and it would go from being aqueous to a solid. So again, if something is normally soluble, but it is one of the exceptions, it goes from soluble to insoluble. And opposite is true as well for the other side. If something is normally insoluble and it's an exception, it will go from insoluble to soluble. And that would be something on this next page here that is an exception type of thing for something that's typically insoluble. So because silver chloride is an exception to the normal solubility, we would get that solid to form there. And when we would mix something like silver nitrate together with sodium chloride, it is actually the silver ions from the silver nitrate. Ultimately, if you do sort of a net ionic equation, it's the silver ions coming together with the chloride ions in this solution when you mix them, and those 2 guys coming together will make this white solid, which is known as silver chloride in this particular case, which is a precipitate, and that is, you know, sort of the basis of those precipitation reactions we talked about a few chapters back when we were talking about types of reactions. Any questions on how to use solubility rules? So basically, again, you can use these solubility rules to determine whether or not, if you mix 2 ionic things together, you would expect either a solid to form, which would get the solid symbol and be insoluble, or if you mix 2 things together, you expect them to be soluble in each other, which means they would get the aqueous symbol. Any questions on that there? So as I mentioned before, solubility is based, there are some effects on temperature and pressure. So for most ionic solids, the solubility does typically increase with temperature. So if you increase the temperature, as I mentioned before, you actually put in a lot more energy in it. And typically what happens is that added energy will allow those solids basically to be able to have enough energy to break apart. Again, most ionic solids are together in a nice organized sort of three-dimensional space. And again, adding more energy allows each of these sort of got particles or ions basically to have enough energy to sort of escape. And when you dissolve it at a high temperature, for example, and you slowly cool it, like I was talking about before, you make this supersaturated solution. As I don't mean to cross it out, but supersaturated solution, as I mentioned earlier, is really a solution where just by the process of how it's typically made, it allows more solute to dissolve because, again, we're increasing the temperature, and that typically increases the solubility of a solute in a solvent. But the process of letting it slowly cool down, like we talked about earlier, when it does so, again, you end up with that solution that has too much solute in it at that temperature. And that's going to create, as I mentioned before, a pretty unstable solution where the solid just needs that little bit of a push over the cliff to basically want to come out of the solution part. Solubility gases decreases, excuse me, decreases with increasing temperature. And that's because gases, as we talked about, are pretty much flying around, right? So if we increase the temperature of a gas, that means they have more energy and they're flying around a lot faster, right? And that means that they won't be around each other for as long, and they won't be mixing around each other for as long. So the solubility of gases will start to decrease when you increase the temperature. Opposite is true if you kind of decrease the temperature. What happens is those gas molecules, I'll just exaggerate here, are now flying around a lot slower, right? This guy is flying around a lot slower, and they're near each other for a longer period of time because they don't have as much energy as they're flying around. So they'll, for the aspect of sort of mixing, they're staying mixed for a longer period of time as well. Now, when we talk about sort of a gas and a liquid part, the pressure has a lot to do with it. So something known as Henry's law is the solubility of a gas in a liquid proportion, and it's proportional to the partial pressure of the gas above the liquid. At higher pressures, you have a higher solubility of the gas in the liquid part. So the soda can is a very common example of that, right? In your soda, right? You have CO2, which is all the bubbles, right? And before you top it, when it's closed, right, there's a lot of pressure in this can. And what that does is it keeps all the CO2 basically dissolved in the liquid part. Remember that pressure and volume are related to each other. Pressure goes up, volume goes down, which means the volume of the gas, it's in a smaller area. It's able to stay dissolved in the liquid part for a much longer period of time. Then when we pop the top, right, and you open your soda, right, you can sometimes see, some stuff coming out. And that's the CO2 gas escaping, basically, right? As you can see over here in this prettier picture. And as you pop it off, you're releasing the pressure, obviously, right? All that pressure that was in that can before is released. The secondary effect of that is you actually made a big hole in the can, right? Which allows pretty much the CO2 basically to escape. And obviously less of the gas molecules will now, under this less pressure, stay dissolved in the liquid part. And that is why, right, our soda eventually goes flat, right? You open a can of soda, you leave it open for a while, you come back to it, you drink it, you're like, oh, that doesn't taste so good. And that's because pretty much you release the pressure, and that made the CO2 molecules less soluble in the liquid part. And you also, again, put an opening in the soda can where that gas molecules can escape. And obviously, at some point, you have very little CO2 in here, right? And obviously, when you taste it, it's going to taste flat to you. So the higher the pressure, you will have a higher solubility of a gas in a liquid. The lower the pressure, the solubility of the gas decreases a lot in the liquid portion. And that's what's known as Henry's law. There's actually a formula where you could calculate the pressure of a gas, and it's known as Henry's law. It has to do with the molarity, the concentration, and the total pressure and partial pressure. All right, let's talk though about solutions and concentration units. So the first few we're going to talk about here are percentage concentration units. The first one is volume, mass to volume. This is sometimes referred to as percent mass to volume, or some people will call it weight to volume. So that's the same as mass to volume. And it is the mass of the solute over the volume of the solution times 100%. So this is essentially almost like density. On top is grams, on the bottom is milliliters times 100%. Typically, we just give the answer usually in this unit. We don't use like the grams per milliliters. We just call it percent mass to volume. If we had a 4.5 mass to volume percent sodium chloride solution, we can't take this sort of percentage and turn it into a conversion factor. Basically, what that would mean is I have 4.5 grams of sodium chloride in 100 milliliters of water, or 100 milliliters of solution, not water. Or you could say in 100 milliliters of solution, you have 4.5 grams of sodium chloride. So sometimes you're given the actual percent mass to volume. And again, you can kind of treat it like a conversion factor, and you could turn it into a conversion factor. And since this is mass to volume, it's the mass on top with the number. And usually we assume 100 milliliters of solution. We assume 100 because it just keeps the numbers the same, right? So just like if you have a percentage normally and you want to turn it into grams, you would assume you have 100 of it. So if you had 5%, it would be 5 grams out of 100. So why don't you take a second here and calculate this? We're looking for the mass to volume percent of a vinegar solution that contains 5 grams of acetic acid in 100 milliliters of solution. So take a moment and calculate it, and we'll talk about it. All right, here. So we're looking for the percent mass to volume. And that is, again, the mass of the solute, the volume of solution times 100%. And vinegar contains 5 grams of acetic acid. So our acetic acid is our solute. We have the volume of solution. So pretty straightforward in this case. We're just going to take the 5 grams, going to divide it by the 100 milliliters, times it by 100%. Should get something like 5% mass to volume. Again, usually we will not use, say, these units in this sort of percentage. We'll just kind of a percent when it's all said and done. So again, what that percentage means is we would technically have 5 grams of acetic acid, like it says in the solution, or in the problem, over 100 milliliters of solution. Or again, if you want to use it as a conversion factor, you would have 100 milliliters of solution and 5 grams of acetic acid. Any question on that calculation there? Another percent concentration that's used a lot, like in percent alcohol, is percent mass, percent volume to volume. And that's basically the volume of the solute over the volume of the solution, again, times 100%. So same thing if we had a 4.5% volume to volume solution of sodium chloride. If you wanted to convert it into a usable conversion factor, that would mean you have 4.5 milliliters of sodium chloride and 100 milliliters of solution. Or in 100 milliliters of solution, you have 4.5 milliliters of sodium chloride. So again, like conversions and doing dimensional analysis, and you can use these percentages again to figure it out. So for example, if we had a bottle of rubbing alcohol, it contains 70 milliliters of 2-propanol, which is also known as isopropyl alcohol, and it's in 100 milliliters of solution. So if we were to calculate the percent volume to volume, again, we want the volume of our solute, which is our 2-propanol. So that would be 70 milliliters. Remember, the solute is a smaller part of the solution, right? Times 100%. And again, if we do that, basically 70 divided by 100 times 100 gets us 70% rubbing alcohol or isopropyl alcohol. And again, we would typically leave it something like this, with the percentage as sort of the units at the end. Any questions on that there? So there's percent mass to volume, there's percent volume to volume, and sort of the third percentage unit that we sometimes come across is percent mass to mass, which is a common sort of unit. Let's take a look at that. We have percent mass to mass. Oops. Let me just add that one in. I think we should have it, but just in case. I think it's coming up, but just in case, we'll talk about it. Percent, we'll talk about it in a second. Why don't you try this example first? A saline solution is used in intravenous drips that contains 0.92% weight to volume sodium chloride. How many grams of sodium chloride are contained in 250 milliliters of solution? So take a moment or two and figure out how many grams of sodium chloride are in the solution. Okay, so here we're given mass to volume, basically. So when we have 0.92% mass to volume of sodium chloride, Again, we can do this sort of dimensional analysis way. You could also plug it into the formula if you want as well. It's basically the same math. But basically what that means is we should have 0.92 grams of sodium chloride because it's mass on top in 100 milliliters of solution. Or you could kind of convert it the other way. 100 milliliters of solution would give you 0.92 grams of sodium chloride. So we're starting with 250 milliliters of solution, and we want to figure out how many grams of sodium chloride. So we do want to use it in this fashion here. That way the solution would cancel each other out. So we're going to take, there are 0.92 grams of sodium chloride in 100 milliliters of solution. The milliliters of solution will cancel each other out, and we will be left with grams of sodium chloride, which is good. And we will end up with, there are 2.3 grams of sodium chloride that's dissolved in the solution. So this is a way, again, you could kind of use that percentage as a conversion factor. You could do the problem as like a dimensional analysis problem. You could also, if you wanted to, really kind of plug and chug into the formula. The mass to volume is the mass of the solute, the volume of solution, times 100%. And if you think about what was given to you, you were given this number, you were given this number. So again, you could rearrange this and solve for the mass of the solute, which, as you will see here, ends up being the exact same calculation as we just did. It would be the volume of solution times the percent mass to volume divided by 100%. So math-wise, it ends up being the same, you know, if you plug it into the sort of formula for it, or if you just kind of do a conversion problem. But again, you could do it either way. You'd get the exact same answer, obviously, because this, again, would be 250 in our example. This would be our 0.92, and then obviously that would be 100, which is the exact same numbers we had when we did it more of a conversion factor way. So again, you don't necessarily have to do it as a conversion factor way. Sometimes it's a little bit easier to follow the units. You could, like a normal sort of formula, just plug everything in there and solve for it. Any questions on that there? Yeah, so weight, volume, and mass volume, they're really the same. Yeah, most people these days call it mass to volume, or percent mass to volume. Yeah. And it is the same as weight to volume, basically. Long time ago, people used to usually call it weight a lot of times, but a lot of books and a lot of people nowadays will call it mass to volume instead of weight to volume. But they are the same thing, basically. In this case, it's basically the mass of the solute over the volume of solution. You know, people. We a lot of times people use mass instead of weight because, you know, usually in chemistry when we weigh out something, we don't usually call it the weight, we usually call it the mass of the item, and stuff like that. But it's basically the same thing. So you'll see it kind of interconverted a lot, but I would say most people kind of moved on to sort of using mass to volume, but definitely people still do use weight to volume. But basically the same thing. It's like if you weighed out how many grams of something. Other questions? All right. So here's the last one I was talking about, and you can see here, this is mass to mass percent. It's parts per million, is it? Do they not have that one? No, they don't. Okay. So this is what is sometimes referred to as parts per million, which is basically the mass of the solute over the mass of the solution times basically 10 to the sixth. You could also do parts per million for volume over volume. So there is a third sort of percentage concentration. I'm not going to worry too much about parts per million here, so we don't worry too much about that for us. but this one you should worry, so sort of similar to what we see here. A third one that goes with percent mass to volume and percent volume to volume. The third sort of percentage one was sometimes referred to percent mass to mass. And that is the mass of the solute divided by the mass of the solution times 100%. So that's a very common sort of percentage unit, which is percent mass to mass. Now, the important part here is the bottom part, and the mass of the solution, you want to make sure when you do that part is the mass of the solute plus the mass of the solvent times 100%. The reason why I say the bottom part here is important, more so than these two guys, which are volumes. In most cases, when you're doing the other two like we did before, they typically will in the problem just straight out tell you, hey, the volume of the solution is this. While when you do percent mass to mass, which by the way, to go back to kind of that earlier question as well, some people also will call mass to mass weight to weight. So percent W to W. But again, most people will go mass to mass nowadays. When you have a problem that involves sort of percent mass to mass, they oftentimes will break that apart. So they'll give you the mass of the solute separate from the mass of the solution, the solvent. So you want to make sure that you add that together. So for example, if we made a solution by dissolving 2.5 grams of calcium chloride and 50 grams of water, what is the percent mass to mass? So why don't you take a second there and calculate the percent mass to mass for that solution. Okay, so if we're going to calculate the percent mass to mass, again, percent mass to mass is going to be the mass of the solute divided by the mass of the solution times 100%. So if we make this solution by dissolving 2.5 grams of calcium chloride in 50 grams of water, in this particular problem, our calcium chloride is our solute, and our water is actually our solvent in this case. So the solute would be 2.5, but we do need to calculate the mass of the solution. And the mass of the solution would be the 2.5 grams, which is our solute, plus the 50 grams, which is our solvent. So our water is our solvent, so we want to add it to 50. And that means that our solution would be 52.5 grams. And in a problem like this, is very common. People will just divide by the 50, thinking that the water is the solution. But again, here it is just the solvent. So very common in these type of problems, it's separated. So you would take the percent mass to mass and that would be our solute, which is the 2.5 grams, divided by the 52.5 grams, which is the total mass of the solution, not just the solvent. And that would give you something like 4.76% mass to mass calcium chloride. So this is a third percentage unit, which is used a lot. And again, is percent mass to mass, or percent weight to weight, is sometimes used to be called. And it's actually a one that's used a lot in terms of sort of concentration units involving percentages, but is the one where really out of those three, you got to really make sure that the bottom part there, that you get both the mass of the solute and the mass of the solvent, and you add them together, because usually in these type of problems, they are given to you sort of separate in terms of the information. And that's a little bit different than the other two, the volume, the ones that have volume on the bottom. In most problems, when you're dealing with something with volume, you would be given just the entire sort of volume of the solution. It's usually not broken up for you. Any questions on those sort of percent units? And again, for us, you don't have to worry too much about parts per million and stuff like that. But you do need to know this one as well. So make sure, again, sort of add it to your list. You do need to know about that. Any questions on that? Okay. Then, since we're talking about concentration, let's talk about sort of the most common unit of concentration that is used, and that is molarity. And molarity is big M, and that's what it kind of stands for, big M. And that is basically moles per liter. And technically it is moles of solute over liters of solution. And you could kind of think of this as a formula where you could solve for any of those things. If I wanted to know the liters, it would equal the moles divided by the molarity. If I want to know the moles, it would equal the liters times the molarity. So this is probably the most common unit of concentration that you will see. If you remember, maybe in the lab, if you looked at bottles, it would usually have like a number with an M next to it, like 8M, 0.5M on the bottle, And the larger the number, the more concentrated the solution is. Sort of the smaller the number, the more dilute the solution would be. So if we had something like 4.5 molar sodium chloride, when you would want to use that in an actual calculation, you would probably want to convert it into more usable units. And that would be the same as saying you have 4.5 moles of sodium chloride in a liter of solution. Or you could use it like a conversion factor, liter solution, there is 4.5 moles of sodium chloride. The number always stays with the moles part, and it's always per 1 liter when you're using molarity. The reason I highly recommend when you do calculations that you convert something like this into both of those units is when people just leave the big M and they want to do calculations, they oftentimes forget all about the liters part. They're like, I'm not sure where it is, I'm not sure how it cancels out or anything like that. So you can use it like a conversion factor to help you sort of calculate something. So for example, if you had 355 milliliters of a 1.25 molar solution of calcium chloride, how many grams of calcium chloride would that be? So to sort of help you through this calculation, we can think about molarity and what was given to us in this particular problem. And if we just sort of scratch off, what was given to us, we don't have liters, but we do have milliliters, which means we can get to the liters. We are given the molarity. So if you weren't sure where to start with, the only thing we don't have is moles. So that's a really good place to start with here. The moles would be the liters times the molarity. So before we could use this, though, we do need to do a couple of conversions. We do need to convert our milliliters into liters. So the first thing we want to do is take our 355 milliliters there's 1,000 milliliters in a liter. That gives it 0.355 liters. So that part's good. Now, when we have something that is 1.25 molar, that becomes 1.25 moles of calcium chloride in a liter solution. Or again, you could use it as a conversion factor in the opposite way, a liter over 1.25 moles of calcium chloride. So now you have everything sort of in the right units. You can see all the units, and really you could treat it like a conversion problem. If I started with the 0.355 liters of calcium chloride, if I just do it like a conversion problem, liters are on top, which means I do want my molarity to be used like this, which is 1.25 moles of calcium chloride over a liter. Liters will cancel, and we will end up with 0.444 moles of calcium chloride. So that's close to what we want, but we do want grams. So very common when you're dealing with molarity, you oftentimes want things like grams, or you're given the information in grams. And we know that if we want to go from moles to grams or grams to moles, the thing that we need to do that is the molar mass from the periodic table. So if we go to the periodic table, it's 4008 for the calcium, and there's 2 chlorines, each at 3545, again from the periodic table. And if you did all that sort of math on the periodic table and got the molar mass for calcium chloride, you would end up with something like 111 grams per mole of calcium chloride, again from the periodic table and the molar mass, right? And if we times that by our 44.4, we end up with 49.3 grams of calcium chloride. First off, any questions on that calculation there before we talk and end here with what it actually all means? So what these numbers means is if you wanted to make this solution that had a molarity of 1.25 molar, you would take a beaker, you would take something, flask, you would weigh out 49.3 grams of calcium chloride into the beaker, the flask, whatever it may be. You then would, since calcium chloride is ionic, probably add some water in there, and that would be your solvent. Right? And obviously the calcium chloride would be your solute. And you would add enough water in there until you got to a total volume of 355 milliliters, right? Give it a mixy, shaky, right? Everything dissolves. Maybe not so much shaky, more of a mixy. And at that point, you would have a 355 milliliter solution that has a molarity of, in our example, 1.25 molar. Any questions on sort of what that means or those numbers mean? Okay, so I think that's a good place to stop. So we're almost through 8. We'll roll through the rest of 8 on Wednesday. We will then go into chapter 9 as well, and those notes will be up there hopefully before Wednesday, and we'll get in there. A couple of things just down the road here. Thinking originally scheduled, I think next week was the next exam. It's going to be moved one more week past that. So let's see here. So originally, I think on the syllabus there and on the schedule, the next exam was scheduled for next week, the week of the 18th. It will actually happen the week of the 25th will be our last exam there before the final. And it will cover through chapter 9. So that'll give us an opportunity to this week and the beginning of next week, finish chapter 9, and that'll give you like a week to study. So the next exam will be moved to the week of the 25th, either the Monday or Wednesday. I'll let you know, obviously, as we get closer which day it will be, but it will be moved that day. I think what we might do next week, maybe on Wednesday, we might have a quiz, and I'm thinking about what it's going to be on. So it'll either be on last chapter in this chapter or something like that. So this coming Wednesday, I'll let you know about perhaps a quiz that we might have next week and what it will be on for sure. But I think we'll probably have some type of quiz next week on these chapters we've been talking about. So maybe the last one, this one, or a couple of those we'll talk about on Wednesday. Any questions on that? Okay, so that'll do it for today. Have a good rest of your day, and I will see you on Wednesday. Thank you, you too. Have a good day, everybody.